Good day, students. Welcome to part 9 of the Algebra 2 Trig Regents review for January 2014. This is the last part in this installment. We're going to be doing problems 37 through 39. If you want to gain access to previously released uh, exam solutions, you can go to mathgotserved.com/testprep.html and you can gain access to 2013 and 2012 questions. All right. So let's take a look at problem 37. It says, because Sam's backyard gets very little sunlight, the probability that a geranium planted there will flower is 0.28. Sam planted 5 geraniums. Determine the probability to the nearest thousandth that at least 4 geraniums will flower. Okay? So we're going to make use of the binomial probability formula. I got this from the Regents Prep website, pretty good website. So this is a formula that we're going to be using. NCR, P to the R times Q to the NR. This is the probability that an event will occur exactly R times. So let's apply this problem to our situation right here. So P is the probability that an event will occur. What event is occurring here? It is the flowering of the geraniums, okay? So P is basically the probability the plant will flower. The plant will flower. Okay, and what is that probability? It's 0.28. That's the probability that a plant will flower. Q is the probability that the opposite happens. Probability the plant will what? The plant will not flower. Okay, so we know that the probabilities always add up to 1. So if the probability that the plant flowers is 0.28, the probability that the plant will not flower is going to be 1 minus P, 1 minus 0.28, which is 0.72. Okay? Alright, so we have our P and our Q down, and R is basically the number of times that the event is going to occur. So if it says at least 4 out of 5, that means, so at least 4 means R is going to be equal to 4 or 5, right? Because there were 5 geraniums planted, and at least 4 flowered. That means either 4 flowered or 5 flowered. So we're going to be computing the probability of these two cases, and then we're going to find the sum of their individual probabilities, all right? So let's start with R equals 4. What does that mean? That means the probability that 4 of them flower, okay? That 4 flowers, 4 geranium flowers. All right, so to compute this, we're simply going to do, let's see, what did we say? N is, we didn't indicate what N is. N is basically the number of the number of flowerings that could possibly occur. Okay, so N is the number of trials. If you think about trials, in this case, trials is attempt at flowering. Okay, so attempt at flowering. In this problem, how many attempts do we have at flowering? If we have 5 geraniums, how many plant geraniums are going to attempt to flower? It's going to be 5. Okay, so N is going to be 5 in this case. All right, so let's apply it to this situation. Probability that 4 of them flower is going to be, let's rewrite the formula again, N CR P to the R Q to the N minus R. All right, note that R is going to keep changing. All right, because we're changing the number of times that we wish to obtain a certain number of outputs. So this time we want 4 as our output. And then when we're looking for 5 to flower, then our R, which is the number of times what we want to obtain, will also change. Okay, so in this case we're going to do n is 5. We're selecting 4. 5, choose 4. And then P is the probability that it will occur, which is 0.28 raised to the R power, which is 4, times probability that it will not occur, 0.72 raised to the n minus r. N minus r, n is always 5, so 5 minus 4 is 1. Okay? One thing you want to note, the behavior of the powers is just like you're expanding a binomial expression. Okay? So this is the probability that 4 of them flower out of 5. We also have to consider R equals 5, which is the probability that 5 of them are going to flower. Basically, everything flowers. If everything flowers, that means none of them do not flower. Okay? So in this case, we're going to have 5 out of 5. We're choosing 5. And then probability that it will flower is 0.28. R in this case is 5. We desire 5 of them to flower. And then 0.72, the probability that it doesn't flower is going to be 5 minus 5, which is 0. Okay? So, since we're doing probability that 4 flowers or probability that 5 flowers, you have to remember that this word or means you're going to add the probabilities. Okay, anytime you see and, that means you multiply probabilities. So do not forget, this is really important. So since it's 4 or 5, because it's at least 4, we're going to multiply these individual probabilities together. So we're going to have 5 choose 4 times 0.28 raised to the 4th power times 0.72. Probability that 4 flower plus 5 choose 5, 0.28 to the 5th times 0.72 to the 0th power. Okay, the reason why I'm writing it like this is because I want to plug it in my calculator. Let the calculator do the heavy lifting here, okay? Let's go ahead and plug that into our calculators. All right, I'm going to be making use of the TI-89. Well, you know what? Let me change this. I'll use the TI-84 instead. All right, so I'm going to use the TI-83. So let's go ahead and enter this expression. The syntax for the 83 and the 84 is similar. That's why I chose to use this as opposed to the 89. Let's see. So we're going to enter 5 choose 4. There are two ways you can gain access to the combination function. You can go to the catalog, second function catalog, and go press N, first N right there, and go to NCR, or you can go to math. Let's click that. You can go to math and then go to probability, and then you have combination right there. Okay, so the syntax is as follows. You have to enter the first number first. I'm going to use parentheses. 5 choose 4, so 5, enter the first number first, and then I'm going to use the math menu. Math, go to probability, option 3. 5 choose 4 times 0.28 raised to the 4th power times 0.72. Alright, this is the probability that 4 of them will flower. So it's either 4 flower or 5 flower. So let's enter the 5 flowering situation. 5, math, probability, option 3. 5 choose 5 times 0.28 raised to the 5th power. This one is going to be 1, right? So we don't have to waste our time with that. So there goes the answer, 0.2384. All right, so let's write it down. 0.2384. Okay, so now, how many decimal places were we supposed to round it up to? Let me get my calculator back up. Okay, I ruined the answer. It's supposed to be 0.0 2384. So point 02384. The problem indicates that we should round it to the thousandths place, okay? So this is a tenth, hundredth, thousandths. So the number behind is bigger than is 5 or greater, so we have to round up. So our answer is going to be 0.024. There you have it. Okay? All right, let's shift our attention to problem 38. In problem 38, it says two sides of a parallelogram measure 27 centimeter and 32 centimeter. The angle, the included angle measures 48 degrees. Find the length of the longer diagonal of the parallelogram to the nearest centimeter. Okay, so anytime you're dealing with any measurement of a shape with the provided measurement values, you want to give yourself a visual. Okay, always give yourself a visual so you don't ruin your orientation in any fashion. Okay, so I want to make sure I'm putting everything exactly where it belongs, so I'm going to make a sketch of the situation. So let me just clone this object right here. Give me 1 second. So let's clone that. I want to make sure it's a perfect parallelogram. All right, and I can just clone this. Okay, so remember parallelogram, opposite sides are parallel. Okay, so in this case we have 27 and 37. It's not drawn to scale. This is 27 and this is 37. The angle 48 degrees. We notice we have two angles here. We have the acute angle and the obtuse angle. So 48 degrees is acute, so we know that 48 degrees goes right here. All right, and that's also 48. The problem says find the length of the longer diagonal. So the longer diagonal is going to be opposite the bigger angle. So this is a longer diagonal right here. Okay, now since this is a parallelogram, we know that these two angles could be viewed as interior, same side interior angles. So same side interior angles of a parallelogram are supplementary. So that other angle right there and this angle add up to 180 degrees. So this angle, how about call it C? Okay, so big C is going to be 180 minus 48, which is 132. So this angle right here is 132. So opposite sides of a parallelogram are congruent, so we know that if this side is 37, this side right here is going to be 37 also. Okay, this is congruent to that, and this is congruent to this. Okay, now let's see. What are we looking for? We're looking for the length of the longest diagonal. So how about we call this little c? Okay, call that little c. Let's call this A, big B. Call this little a and call this little b. So in this problem, we're to find little c. Okay, so in this situation that doesn't involve a right triangle, we can either use law of sines or law of cosines. So which one are we going to use here? Now let's look at what we have. We have two sides and an included angle. That is S, A, S. Please keep track of the order. Two sides and the angles between the the angles between the two given sides. So anytime we have SAS, you always use the law of cosines. Okay, law of cosines. There are three variations to the law of cosines. You have a squared equals b squared plus c squared minus 2bc cosine a. This is the one that's provided on your reference sheet, but there are two other variations. B squared equals a squared plus c squared minus 2ac cosine big B, and the last variation is c squared equals a squared plus b squared minus 2ab cosine big C. All right, so which of these three is applicable to this situation? We have big C here, The only formula with big C is this one right here. So that's the one we're going to use, okay? So to find big C, to find little c, we're going to write c squared, little c squared, equals, a is 37, okay? So we have 37 squared plus b is 27, 27 squared minus 2 times 32 times 27 cosine 132. Okay? If you plug this into your calculator, you're going to have 2,909.26. And then to get c by itself, you simply take the square root of both sides. And then when you take the square root of both sides, you're going to have little c equals, you're going to have 53.940, 53.9409. All right, but we were to round it to the nearest centimeter. So c is going to be 54 centimeters to the nearest centimeter. Okay? All right. All right, so for 39, it says solve algebraically for all values of x. Log base x plus 3 of log 2x plus 3 plus log base x plus 3 of x plus 5 equals 2. So the first thing we're going to do here is we're going to condense these, the logarithmic terms on the left side, and we're going to use the addition property of logarithms, okay? So basically, if you have the sum of two logs with the same base, it's the same thing as the product, the log of the product of the logarithmic argument. So if you remember log base b of x plus log base b of y, you have the sum of two logs with the same base is the same thing as the log of the product of the logarithmic argument x times y with the same base. All right. So you notice that these two logarithmic terms have the same base x plus 3. So these two can be condensed into log base x plus 3, the base stays the same, of the product of the logarithmic argument. So we're going to multiply 2x plus 3 with x plus 5. All right, so it's going to be 2x plus 3 quantity times x plus 5 equals 2. All right, so let's pull this out. The term, the logarithmic arguments, it's product of those two binomials. So x plus 3 base, and then if you do first, 2x squared plus 10x outer, inner, 3x last equals 2, okay? Now let's combine like terms. These two terms are similar like terms. So we have log base x plus 3 of 2x squared plus 13x plus 15 equals 2. Now, to get rid of this logarithm right here, we're going to exponentiate both sides using the base of a logarithm as our basis of exponentiation. If you remember the exponent property of logs, if you have something like this, a to the log base a of x, these two cancel out since exponents and logs are inverse operations, and you're left with x. So this is the setup I want to achieve here so I can eliminate this log, okay? So what I'll do is I'll look at the base. The base is x plus 3. So I'm going to exponentiate both sides of my equation, all right? So I'm going to put a big x plus 3 here and a big x plus 3 here. And I'm going to exponentiate both sides, okay? So to preserve equality, whatever you do to the left, you do to the right. So on the left side, we have log base x plus 3 of 2x squared plus 13x plus 15. And on the right side, these two gets exponentiated. So quantity x plus 3 squared. All right, now what does this help me achieve? Well, this two are inverses, so they cancel out. On the left side, just like we had here, you notice how we had a and log base a cancel out because this exponent had the same base as this logarithm. So the base of this exponent is the same as the base of the logarithm, so they cancel out. And on the left side, we're going to be left with 2x squared plus 13x plus 15. And then if you do x plus 3 times x plus 3, if you expand that, you're going to have x squared plus 6x plus 9. All right, so now we're going to set it equal to 0. Put the quadratic equation in standard form. So I want to move everything to the left side. So if I simplify that, I'm going to have x squared plus 7x plus 6 equals 0. All right, so now let's solve this by factoring. So I'm going to use the x game here. Set up my x. AC goes on top. AC is 6. B goes in the bottom, 7. Two numbers that multiply to give you 6 and add to give you 7, 1 and 6. Now, since a is 1 here, we do not have to factor by grouping. We can jump straight to the factored form. X plus 1 times x plus 6 equals 0. Now, using the zero product property, we have x plus 1 equals 0 and x plus 6 equals 0. So our potential solutions are x equals -1 or x equals -6. Now, there are domain constraints on the inputs of a logarithmic function. So the argument of a logarithmic function is defined for only when the input is greater than 0. Okay, so log base b of x is defined for when the argument x is greater than or equal to is greater than 0. If you take the log of a negative number or 0, your output is going to be undefined because you're outside the domain of a logarithmic function. So we have to ensure that these two answers are in the domain, or else it cannot be considered as a solution. So there are two ways we can accomplish this. We can plug in these two values into our logarithmic arguments to make sure they're positive first, or another way we can do this is by solving for the domain constraints and looking for the intersection of the two to see which of our solutions fit into the acceptable domain. All right. So whichever one you want to use, I'm going to do the second method. I'm going to extract the two logarithmic arguments. I'm going to set up the domain constraints and look for the intersection of our domains, and that should be the acceptable domain for our solution. All right. So our two logarithmic arguments are 2x plus 3 and x plus 5. Now these two must be greater than 0. Remember, you cannot take the log of a negative number or 0. So let's solve for x here. If I solve for x here, I'll have 2x is greater than -3. Hence, x is greater than -3 over 2. -3 over 2 is just 1.5. So x has to be greater than -1.5. And then for this one, x has to be greater than -5. Now, what's the intersection of these two? To help you visualize it, let me use a number line. So let's draw ourselves a nice little number line here. So this is 0, 1, 2, 3, 4, 5. -5. So the constraint on this this argument is that x has to be greater than -5. So from here on out, anything to the right of -5 is acceptable to the first one. All right. The second one, x has to be bigger than -1.5. This is -1 right here. This is -1.5. -1.5. So let's go ahead and graph it. So we have -1.5. There, anything to the right of that. Okay. So what we're going to do is we're going to find the intersection of these two. The intersection of these two will be the acceptable domain for our solution. So if we intersect these two, you're going to go from -1.5 to infinity. Okay? So what I'm saying in essence is any value must satisfy both of them. That is why we're basically looking for the intersection. All right, let's graph our solutions. The first answer we had is -1. -1 is right here. Bam. That is perfect because it's within our acceptable domain. All right. How about negative 6? Uh-oh, negative 6 violates both of them. That's way out. Okay? Even though it violates only one, that's unacceptable. But this is so bad it violates both of them. So what does that mean? It means that this solution right here is extraneous. This is not a solution, not a solution. The only acceptable solution is x equals negative 1 because it does not violate the domain of our solution, which is x has to be greater than negative 1 and 1/2. All right? So that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to our channel for updates to other cool clips such as this. And please post a comment to let us know what you think about this clip. More clips can be found on mathgotserved.com/testprep. Thanks again for watching.